Hello everyone, welcome to Bad Boy Calculus. Today we're going to talk about logistic growth model. A logistic growth model looks like this, where you start on the starting point green, go to halfway point A/2, which is your fastest growth rate point, and you're going to head upward to your carrying capacity, the red one. The differential equation of a logistic growth model is dP/dt equals to Kp a minus P. There is another form of that, but I generally just use this one. You don't really need to know both forms. So the A right here you see is the same thing as your carrying capacity, which is your horizontal asymptote. The K right here is what we call a proportionality. So what it does is it's going to control how fast this graph grows. So for something that grows faster, like mosquitoes, or maybe like Indians, they are gonna have a big K. But something that grows slower, like panda, then the K will be smaller. It doesn't really affect how your graph looks like. The shape generally still looks like that. Now, the next thing you want to know is that if I do integrate it to get P equals to, I'll get an equation of A over 1 plus CE negative AKT. The first thing you want to notice is there are two A's right here, and they are exactly the same as the A on top, the red boxes. There is a K right here, which is the same as your K on the top equation, the pink box. So you also notice there is a C right here. So what does that do? Well, it doesn't really do anything, but this green box, A over 1 plus C, will give you your starting value, A0. So let me show you how the math works. For example, we have equation of dP over dt equals to 20p minus 0.1p squared. And let's say I gave you an initial condition of A0 equals to 20. The first thing you want to know is that you want to get this into the form of dP over dt equals to Kp a minus P. So what you need to do is you just look at this back number right here, and you want to divide it by the whole thing except 1p. What does that mean? You divide by 0.1p instead of p squared. And you're going to do that to both of the terms. So my equation right now will look like dP over dt equals to 20p is going to be divided by 0.1p, and minus 0.1p squared is going to divide by 0.1p. Now, put 0.1p on the outside, so it kind of cancels out the division. The next thing you want to do is you want to put the 0.1p back in the front. That will simplify into 200. That will become minus p. Exactly what we want. There's a right here. That's this number. There is a number in the front, k. That is this number. And you can see the rest of the equation matches. They look exactly the same. So now that I have found what K and A is, let's write it down. A is equals to 200. And K is equals to 0.1. And don't forget that we have an initial value of 20. So let me just write it in green. A0 equals to 20. We're ready to write the equation for this differential equation. So what we do is we're going to move down to P equals to A over 1 plus CE negative AKT. Plug in your A, which is 200, over 1 plus C, E, negative 200. K is 0.1, T. We'll go ahead and simplify the bottom a little bit. 200 over 1 plus CE, negative 20T. Now again, how do I use my initial value? It's just the front right here, these three guys right here. So those are going to give you 20. 20 is equals to 200 over 1 plus c. And then we're going to continue by solving what c is equals to. You can multiply the whole thing, 1 plus c over, and divide the 20 over. So you have 1 plus c equals to 200 over 20. 1 plus c equals to 10, which will give you c equals to 9. We're going to plug it back to the equation of a p right here. Now we have a very beautiful equation. P equals to 200 over 1 plus 9 e negative 20 t. Here we find the equation of the logistic growth model. Now let's go ahead, graph it, and see how it looks like. First of all, your starting value was 20, and you can again confirm that by doing the green part right here, 200 over 1 plus 9, which gave you exactly 20. So we're going to start at 20. The carrying capacity is the number on top right here, which is 200. So go to 200 and draw a horizontal asymptote, your carrying capacity. Half of that, which is 100, is what we call the fastest growth rate. So right here is where your graph changes concavity. From green to yellow, you are going to graph it concave up, which is part of a happy phase. Here's how a happy phase looks like, concave up. The second part, when you go from yellow to red, is going to be increasing concave down, which is part of a sad phase, concave down. That's how, in general, this graph looks like. Now, sometimes your initial value is not below the yellow point. Let me show you an example. If your green point starting value is not below the yellow dot, say for example your carrying capacity is 200, your halfway point is 100, and this time your starting value is 120, then what you will need to do is you simply go concave down, upward. Now, there's also a situation that maybe your starting point is above your carrying capacity. So in here, we have a carrying capacity of 200. Again, your halfway point is 100, half of 200. If your starting point is above it, then what you need to do is you're going to graph it concave up, part of a happy phase, and track back down to your carrying capacity. You can see that no matter the situation, your graph always trend back to the red one. And that is something that the AP test really like to test people. So you need to remember that limit time approaching infinity of your graph P, no matter where your initial graph is, as long as it is a logistic growth model, you will go to A, which is your carrying capacity. That's basically all you need to know about logistic growth model for the AP BC test. If you have any question, you can leave the question in the comment. And if you like this video or you want to learn more calculus with me, hit the like button and subscribe. I will see you in the next video.